I think we arrived at the last talk of the school for this week, which is also Michael Wheeler's last talk for this school. So Michael, please go ahead.
Okay. All right, so I thought I'd start today basically just by sketching the proof of the identity that I stated right at the end of the last lecture. So just to remind you, that was this summation identity that holds between basically the family F mu and G mu, where you get a nice factorized right-hand side, but it's not the sort of typical form that you see for a Cauchy identity, because this is some sort of non-symmetric kernel. So let's just do the proof of that for completeness. So this strategy will be very similar to the proof that we did for the other summation identity. So in the first step, essentially you write down the left-hand side, which is this sum here, and then you want to represent that thing as a partition function, and the argument is very analogous. So I will consider this sort of enlarged partition function here, where I have this sort of extra piece that has zeros entering it and also exiting it. And then I'll set up the remainder of the lattice basically with the boundary conditions that could reproduce this sum. So that's going to be having the colors 1 up to n entering along these edges here, and then colors 1 up to n exiting along these edges. And of course, we have to have conservation, so I have each of the colors entering and exiting, so I should make sure that everything else is all zeros. So that's the setup, and the claim is that this partition function, even though it has this this extra piece here, so this sort of adjoined cross, the claim is that this partition function still faithfully reproduces this sum, and the argument is exactly the same. So basically, last time we argued that it would be impossible for a path to make its way. Well, in this case, they can't actually come from the bottom. They would have to come, say, from the left. So basically, it should be impossible now for a path to make its way all the way across the lattice and then into this external piece and then back. So we're claiming that in the limit where the lattice becomes infinitely large, this is an unfavorable configuration. So with that one caveat, you can indeed represent this sum in this form. And then we just use the Yang-Baxter equation to bring this cross that sits on the right all the way to the left. And the result of doing that is this picture here. I could have said as well that in the picture on the left here, so clearly along these middle edges, I have S1, S2, S3, where S1, S2, S3, this is the string that represents mu. So clearly the bottom half here is reproducing F mu, and the top half is reproducing G mu. All right, so then on the right-hand side, let's just fill in our boundary conditions a little bit. And so now, actually, if you look at basically all of this lattice here, it's actually completely frozen, completely trivial. So what happens is the following. So again, in this sort of top region, I have all zeros exiting from all of the edges. So that will force all of the incoming edges for that region to also be zeros. And then that whole region just freezes with weight 1. And likewise at the bottom now, I'll have some region here, which is again entirely populated by zeros. So basically all of that will just completely freeze out with a weight 1, and then you're just left with this cross here on the left. And that's a little bit more interesting. So again, I have the colors 1 through n entering here, and the colors 1 through n exiting at the top. And so now it's just a pretty simple combinatorial argument to actually keep track of what each of these colored paths has to do. So for example, if I look at the path here of color n, so it actually has no choice. It has to travel straight across until it gets all the way to the final column, where it will then turn upwards like this. And likewise, for the next one, which will be n minus 1, it's going to have to travel straight across and then get up like this. Now, of course, you can't have more than one color on any given edge of the lattice. So it's just completely frozen all the way down to 1, where it goes like this. So you get this kind of triangular pattern emerging from the paths. And if one goes ahead and actually computes the weight of this region, you will observe exactly this product here. Okay, so that's how you prove this identity. Okay, so maybe just a small remark about that. So as we've stated it here, we're given the sort of completely colored version or like rainbow version of this type of identity. But one can think of performing some sort of symmetrization of the colors and using the color blindness theorem to see what you can actually project down onto. And so in particular, for this identity, it's possible to take the colors 1 through n that exit through here, and we can perform symmetrization over those. So basically, instead of having 1 through n, I would look at all possible permutations of those colors and just perform a sum over all possible ways of permuting them. So if you do that, this piece here, in general, will not be frozen. So as you start to permute the colors, it becomes progressively more complicated. But one thing that is true is that if I sum over all such permutations, then this piece here will become completely colorblind. And what you'll end up producing at the end of the day is just a cross that looks like this, that has all ones entering and all ones exiting, like this. And then zeros coming in here and zeros exiting there. So this is just a remark that there is a symmetrization which will project you down onto this object. And this is nothing but the famous domain wall partition function in the 6-vertex model. So all of this machinery has some pretty nice projections onto SL2, and one can recover various known summation identities from previous works. Okay, so just before I go on, any questions? I'm about to leave behind the summation identities. Yep.
Yeah, I have one question. So you wrote that the left-hand side is G mu, but it's actually G star mu. And where did all these factors of Q minus 1, I mean, I can understand the Q's coming in some way, but where did the factors of Q minus 1 go?
Yeah. So basically, if you go ahead and compute this product here, which I'm hoping to avoid doing because it's a bit tedious,
Sure.
basically it will have all of these type of factors. It will have something like, I'm trying to get it right. So probably the inverse of what it's supposed to be. So something like this. So basically you will see that when you compute this thing, there'll be this kind of common factor in the weight of this region. And so once I then divide by that, you'll get, well, on the left-hand side, you'll get G star, and on the right-hand side, you'll get a simpler, basically what it's supposed to be.
Yeah,
So it's just the Q factors are in this, are basically in this. They're in there naturally. Yeah.
I see. And the Q minus ones come from some of the vertex weights.
Yeah, that's correct. Yeah. So they're
Okay.
indeed. Yeah. Yeah.
Okay, thank you.
Okay. All right. So in that case, we'll start with the I guess the final lecture. I'm not going to get up to everything that I hope to talk about, but I think it will still be reasonably complete in a sense. So yeah, the first thing I want to talk about is we could call a recursive construction of the family F mu. Okay, so what I mean by recursive construction is it's a procedure where you specify one of the members of the family. So mu here is ranging over all strict compositions. So I'll explicitly specify one of them, which I can call the initial condition. And then there's going to be an operator that acts on that. And in this way, you can generate the entire family. So it's a sort of purely algorithmic way to generate the functions that you could just do on a computer, for example. You don't need the actual vertex models. But the proof of this recursive construction comes from the vertex model. All right. So let's begin with the initial condition. So I'll call this, this was basically supposed to be in the last lecture. So I'll call it still proposition one. The proposition one, so I fix a strict composition delta. And so delta is being used here because I'm going to assume that the elements are increasing. So delta 1 less than delta 2 up to delta n. Okay, so if I have such a strict composition, then I have the following explicit formula for F delta. F delta is going to be a product from I equals 1 to n, and then a second product from j equals 1 up to delta I minus 1. And then there's going to be a ratio here. So this will be 1 minus yj over xi. 1 minus q yj over xi. And that's multiplied, maybe I'll just put a little bracket around that. That's multiplied by 1 minus q y delta I divided by xi. And then 1 minus q y delta I divided by xi. And just to remind you, the x's, of course, are the horizontal variables, and the y's are the vertical variables of the f function. Okay, so the proof of this is actually very, very similar to what I was just talking about here. So in a sense, perhaps good that we didn't do that explicitly, because we're about to see how it works anyway. Okay, so basically you draw the partition function representation of the function. And because of the increasing property of the outgoing colors now. So remember from last time, these are the coordinates. of the outgoing colors. So what this is saying is that color number 1 has the smallest coordinate, and then color number n has the largest coordinate. And so actually, that fact alone will cause a freezing of this quantity, because somewhere in here I'll have color 1, which exits, and then somewhere else I'll have color 2, and then somewhere else finally color n. And so what happens from making these assumptions is again just the total freezing of the object. Something like this. Okay, so I'll just put a remark behind here. So F delta freezes due to the increasing property of delta. And so it only remains to work out the weight of each of these rows of the lattice. So basically, row number I will correspond to the ith term in this product here. So let's just have a look maybe at row number I. So row number I is going to look something like this. So I'll have one path, which is basically the path of color I. It comes in like that, travels all the way across, and then turns. And it's going to turn in the column where it ultimately exits. So this is color I, and it's exiting in column delta I. Now, before it gets there, it's going to potentially cross a number of other paths. So I could have here maybe some other paths which have smaller index. But actually, in terms of the vertex weights, you see that it actually makes no difference, because the type of vertex that you have is always of the form I traveling horizontally and then crossing another one, j, where I is always strictly greater than j.
Sorry.
Doesn't matter. Yes?
Sorry, I'm a bit lost in your first comment about freezing. Why is it that the one arrow, why can't it make like small like staircase type shape jumps before it gets to the top?
Yeah, so if you actually do the freezing in the reverse order, so start with color n. So color n clearly has no choice in what it does.
I see.
And in this way, you freeze the object. Yeah.
Thank you.
So yeah, just to remark that this row I of the lattice, all of the vertices will have either this form here, whose weight you can compute, or it will be basically of the form of the final vertex here, where you have I and 0. And working out those weights explicitly, you will see exactly this factor here. So this is basically the product of vertices of this form. And this factor here is coming from this vertex here. Okay, so I'll just copy those underneath so that well, that's basically the proof. All right. So that's going to be the initial condition. We're in the situation where, for this family F delta, supposing I'm going to fix, the values of the coordinates of the particles. I'm not going to say anything about how they're ordered, but I'm going to say where the particles have to go out. Right? So we're in the situation where if they're strictly ordered, strictly increasing, we can actually say what the function is explicitly. What we would like to have now is some sort of operation that allows us to move these colors around. So basically, for example, exchange 1 and 2 here, or maybe exchange 2 and n. The positions will remain fixed, but the colors will exchange. So this is the kind of exchange relation that we will seek. Okay. So before we come to that, just a small definition. So this is the Hecke algebra of type an-1, and that's the following. So the Hecke algebra of type an-1 is basically given by a set of generators I, with I going from 1 up to n-1, which satisfy the following relations. So there is first a quadratic relation, ti minus 1 times ti plus q is equal to 0. So that's for all I. Then there is a term with 3 t's. So ti plus 1 ti is equal to ti plus 1 ti plus 1. A kind of braid type relation. And finally, if I have ti and tj, which are separated by a distance of more than 1, the indices, then they commute. So this is for ij strictly bigger than 1. And so the Hecke algebra is going to show up here because there is a very well-known representation, which is in terms of so-called demosuralistic operators. So it has a polynomial, it's called polynomial representation. In terms of these demosuralistic operators. And so the way those work is I'm going to identify ti now with the following objects. So I'll take ti to be equal to q minus the ratio xi minus qxi plus 1 over xi minus xi plus 1. And that's multiplied by 1 minus si. So this thing has an action on functions in n variables. And the action that's happening here, this is just acting as the identity. And this is the simple transposition of the two variables xi and xi plus 1. And it's called polynomial representation because when you act on polynomials, it preserves polynomiality, even though a priori it looks like it should give you some rational function. But we're not going to be acting on polynomials. We're going to be acting actually on rational functions. So the polynomiality is actually somewhat irrelevant for us. Okay. So let's now state the result.
Michael, could you
Yes.
please give an example of how it works? I don't really understand how you can do subtraction between identity and simple transposition.
So let's do a small example. Okay, so let's take T1 and we'll act on just the polynomial x1. Okay, so this should be, so from the first term, it's just q times x1. And then for the second term, I'll have x1 minus qx2, x1 minus x2. And so for this part here, the identity, that's just the function itself, which was x1. Now the transposition s1 will send x1 to x2 now. So I have x1 minus x2. So this is kind of the point. You always, whatever you generate here is always going to be divisible by this. In this case, they actually divide out perfectly. So I have here qx1, they cancel off completely. I have minus x1 and then plus qx2. So if all is correct, it's going to be q minus 1 x1 plus qx2. Does that clarify?
Yes, thanks.
Yep. So in particular, the action of the TIs is only interesting on non-symmetric functions. So if I act on a function that is symmetric in x's, so the action of this part is always happening first. If I act on a function that's symmetric, then that underlying part will just give me 0. So basically, all of this part of the operator goes away if you act on a symmetric function, and you just get a constant times the original function. So, okay. So let's do now proposition number 2. So the following is true. So I'll fix again, fix a strict composition mu1 up to mu n. I'm not saying anything about the relative ordering of the parts of mu, except for one pair. So I have a strict composition and an integer I from 1 up to n minus 1, such that mu I is less than mu I plus 1. Okay, so the rest of the composition can be absolutely anything, but I will insist on the relative ordering of these two parts. Okay, so then there holds the following, that the action of Ti on f mu gives me f mu back again, but where I switch 2 of the parts of the composition around now, which is exactly what we wanted. Okay, so this is where SI mu is basically the original composition, but now I have mu I plus 1, mu I. So the ordering of those two parts is exchanged. Okay, so in terms of the partition functions, it's basically going to be, you have your lattice parts that are exiting. So let's just have a very quick sketch just to illustrate. So somewhere I have color I and color I plus 1 that enter from the left. And well, maybe let's give them a different color. Maybe that's not so clear, actually. Green. All right, so these are the colors that I'm interested in. And we're told in the statement of the theorem that mu I is less than mu I plus 1. So that means that the coordinate of color I, maybe it's here, but it has to be less than the coordinate of color I plus 1. So color I plus 1 is maybe out here. And in particular, they don't even have to be nearest neighbors. So they can be separated by an arbitrary distance. And what this theorem is saying is I take this thing, I act with Ti on this object, and I'm going to get basically the same lattice like this, but where I switch only those two colors. So they still go to the same positions, but the colors get exchanged. So this is what we're trying to prove. All right, so let's do the proof. All right, so it's no surprise that the Yang-Baxter equation will show up in the proof of this statement, but it sort of shows up in a kind of let's say, well, it's kind of circumventing the actual thing that we're trying to prove in a way. So it's playing a role, but it's sort of in the sidelines a little bit. So let's see what happens. So I'll have my my lattice. And the first thing I'll do is just put a cross here. Okay, so I'm actually not I'm not saying that this is equal to anything at this stage. I'm just saying let's consider this picture. And let's now fill out the boundary conditions. So here I'll put I plus 1, color I plus 1, and here this can be color I. Maybe I should keep those in black because it might get confusing otherwise. And the spectral parameters will still be in red. So this one I'll make xi, and this one I'll make xi plus 1. So those are the two spectral parameters that we care about somehow. So I'll only write those ones. And on this edge, I'll have just all zeros, as usual. Okay. And furthermore, somewhere at the top, I have my color I, and somewhere at another position, I have color I plus 1. And this is all of the information that we will be concerned with. So, of course, there are all the other colors as well, but we won't see them in the course of the proof. All right. So this picture that I have drawn, I can basically expand over the possible configurations for these two edges here in pink. So if I do that, I'll get a sum of two terms, which will be the following. So I'll have this vertex, which has I plus 1 and I entering. And let's suppose they exchange positions. Okay, so we have this. So the weight of that vertex times the rest of the lattice. And in order to make the picture consistent, this needs to be I, and this needs to be I plus 1. And furthermore, this spectral parameter here is xi, and this is xi plus 1. Notice that the spectral parameters switch when they go through the vertex. So this becomes xi, this becomes xi plus 1. Okay, so I have that. And I can go ahead and actually explore it. record explicitly the weights of these things. So this vertex here has following weights. So it's 1 minus xi plus 1 divided by xi over 1 minus q xi plus 1 over xi. And the function that I get here is very similar to the f function that I started with. In fact, it's almost identically the same. The only thing that has changed is that I and I plus 1 have switched their ordering here at the left. So this function, I'll give it a shorthand that we haven't used before, actually. So I'll continue to call this f mu in the x's. But I'll put a little superscript here, si. And that's just to indicate that those two colors have been switched at the left boundary. So there is that. And then I need to repeat this process for the other possible configuration. And for the other one, the colors head in the other sense. So this one becomes I plus 1. This becomes I. And that then means that here they're ordered in the traditional way. I plus 1 followed by I. And if I go ahead and work out the weight of the vertex, I get xi plus 1 over xi times 1 minus q over 1 minus q xi plus 1 over xi. And the function that I have here is identically just f mu. All right, so far so good. And then, of course, in the next step, which will surprise no one, we're going to use the Yang-Baxter equation. And so the vertex that was introduced in this picture up here will now be pushed towards the right. And eventually, it's going to emerge from the right edges here. So after doing that procedure, after doing these many steps, you end up with just this. So that vertex emerges here. And it emerges with just zeros as the outgoing edges, which means that these are forced to be both 0 by conservation. And then what has happened for these rows? Well, xi and xi plus 1 actually switch their places. And this color here is still I, and this is still I plus 1. So the result of doing that is actually equal to f mu in the alphabet where xi and xi plus 1 have switched. So it's basically this, but where I act with the operator si. So just the simple transposition of xi and xi plus 1. It may be less confusing actually to actually put that into here. So I'll just write si acting on x here. Okay. So this is the identity that we have proved. So just stripping it down to the actual functions themselves now, we have that this thing plus this is equal to this. So this begins to resemble very closely the Hecker generator that we defined just above. You can even see that some of the elements are matching. So there is here a transposition of those two variables, xi plus 1. And furthermore, the type of functions that are showing up in these ratios resemble very closely what you have in the Hecker operator. So I will not do the explicit next steps, but basically just by a bit of bookkeeping now, one shows that this is equivalent to the following. So this is equivalent to the statement that Ti acting on F mu is equal to Q minus 1 F mu plus F mu Si. Okay, so hopefully you can believe that you go ahead and explicitly compute the things that are here. It is completely equivalent to the equation that is in the green boxes here. All right, so this is not bad, but this is not yet. So this is not yet equal to actually what we want, and what we wanted was F mu, but where you permute the two parts of mu. So basically, the proof of the proposition will boil down to establishing this equality here. But the good news is we've actually already proved this statement, and this was done in the problem session a couple of days back. So if you look at actually what you're trying to prove here, I'll just draw them as maybe some rectangles. So let's just consider what do I want to say? Let's take this equation here and rearrange it. So this rearranges to Q times F mu plus F mu Si needs to be equal to F mu plus F Si mu. That's what we need to show. And so let's see if it's true. In particular, this is a statement that you see there are no coefficients of x or anything funny like that. It's just purely a statement on the partition functions themselves. And well, this is basically what you're going to have. So on the left-hand side here, what am I actually doing? So I'm basically permuting the colors. But one of them is going to be the color I, and the other is the color I plus 1. Okay, so basically I take such a thing and multiply this by Q. So this represents the first term. But then I need to add to it the one where those two colors switch their places. So this is I plus 1 and this is I. And that represents this term here. And notice that where these paths go out, well, they go out at the same positions in both pictures. Always with the red going before the green. So that's the left-hand side. And this thing is supposed to be equal to the right-hand side here. And that one, that's very similar. So for that one, what will change? This is what will change. So they have the same incoming states, I plus 1, but what changes is the relative ordering of the two colors at the top. And so basically the statement boils down to whether these things are equal. And we showed, in fact, that they are equal. So this is true because both of these are colorblind objects. Both are colorblind with respect to I and I+1. But I still have other colors in there, but there's this symmetrization that's happening over I and I+1 that basically merges them into the same color. And so this completes the proof. Okay, so that is maybe one of the more complicated ones we proved. So if there are any questions there, please go ahead. Okay. All right, so in the remaining, I guess, 15 minutes or so, I wanted to say something about orthogonality of these functions. So really one of the main features of this little f and little g is they have an orthogonality property, which is kind of a typical thing that you have when you deal with multivariate symmetric functions or non-symmetric functions. So yeah, let me try to give the statement of the fact. Okay, so orthogonality. So it will be expressed in terms of a certain scalar product. So let's give the definition of that. So in what follows, let's let capital psi.
Michael?
Yes.
Somebody seems to have a question in the chat and they can't seem to hear him.
Okay, I'm not sure if that's true. So if yeah, I actually can't hear. Yeah.
Okay, just one minute.
Oh, I can hear you now. I can hear you now. Yeah.
Can you hear me now?
Yeah.
Okay, okay. So I was trying to ask a question about the previous proof. Sorry. Can you scroll up to the first figure? I'm just a bit confused about notation. Thanks, Sanjay.
Which figure exactly? Further up?
Further up, yes, please. The first, yeah, this where you added the cross.
Yep.
So I thought, according to your convention, I is when you add your spectral parameters, your I is below your I+1, right?
Yeah.
But
I mean this picture here is kind of an auxiliary thing. So I'm not saying this is related to anything. This is just something that you can dream up and then see what is it actually equal to. So it's true that here there's a kind of strange ordering of the spectral parameters, but I'm free to do whatever I want with those. So.
Is the left-hand side just f mu, or is it f mu with the xi and xi+1 interchanged?
So this quantity here that we're starting with,
yeah.
Once you expand over the pink edges, so the pink dots,
yes,
you get these two terms here.
Right, I understand that.
And those are both f where the x's are in the correct order. The point is that even though the x's here come in, with their order kind of switched, this xi is really going here.
Yeah.
And xi+1 is going here. So they look like they're switched, but they're actually not.
But they are switched in the left-hand side, right?
Oh, you mean in the right-hand side?
Oh.
You mean here?
No, no, in your first figure.
In the very first figure, yeah. So here there, what's written here is correct.
But then I'm confused as to why I and I+1 are out of order. No, I should be below I+1 to the right of the cross, and therefore.
I'm not claiming that. So this funny object here with the cross.
Yeah.
is a new object. It's not. It should not be related to anything we've seen so far.
Oh, I see.
So I can make any choice for.
Oh, I see. I see. Okay. Okay.
Yeah.
Got it. Yeah.
Yeah.
Thank you. Yeah.
Yeah. Okay. So yeah, the orthogonality. So in what follows, capital Psi and capital Phi, these will be two multivariate rational functions in n variables. And we're also going to think of the, so in all of this business, there is the secondary alphabet of y parameters that are the vertical line parameters. We're also going to think of these now as being fixed to some definite complex values. Okay. I'll just put that as a remark here. So from now on, consider this alphabet y1, y2 to be some given complex numbers. And in fact, we're actually going to assume that they're all very close to each other, and so we actually make quite a lot of assumptions about these y parameters. The point being that the statement we're about to give is an algebraic statement. So it's sufficient to prove it with all of the parameters taking values in some compact sets in the complex plane. And if you then prove it with variables ranging over appropriate compact sets, you can prove it for all values by analytic continuation. So just to say that such an assumption is going to happen. Right. So then we will define the following scalar product. Which is capital Psi times capital Phi is equal to, or defined to be, 1 on 2 pi I to the n. And then I'm going to have n-fold integral over the x parameters. And this is over some contour C, which I'll give in a moment. And then the integral has the following factors. So it has, first of all, this product here, which is basically a Vandermonde divided by a Q Vandermonde. So this product I and j going from 1 up to n. And then you have your two functions. So the first one will be psi with all of the variables inverted. And then the second one is phi with all of the variables in the usual sense. And this is where the contour C has the form. This is my complex plane. And C is going to be something like this. So some positively oriented contour, which will enclose the point 0, and also, as I said, all of these y variables now, we can imagine they sort of cluster together into some compact set. So this is going to be the points the points yk inverse. And somewhere else outside of the contour will be the images of all of these points under multiplication by q inverse. I'll have something like this. So I'm assuming here that absolute value of q is less than 1, which is consistent with how we've done things earlier. And so clearly, so this is C. So then the image of C under multiplication by q, that's you can think of it as going to be a contour like this that lives inside of the original one. Okay, so that's a contour. And the only reason why we care about whether the points yk inverse are enclosed or not is ultimately we're going to find that those things are the poles of the functions that we look at. So, okay. So that's going to be the scalar product. And then one has the following proposition. I forget what number we're up to, but it doesn't matter. So the scalar product, or rather I should say the Hecker generators have the following self-adjointness property. With respect to this scalar product. So that's the following. So if I act with tk in the first argument, and I leave the second argument intact, that's equal to leaving the first argument intact, and then instead acting with another operator, which I'll call tk tilde on the second argument. And this holds for all k from 1 up to n minus 1. So I didn't define the tk tilde. So tk tilde is just the original Hecker operator, but where I switch xk and xk plus 1. So I've done that correctly. It should just be this. And then 1 minus sk. Sk being the transposition operator. Okay. So that's the claim. And the proof of this is basically by direct computation. So I'm not going to give the proof in view of the time constraints. But basically, you just feed in directly your tk action of tk on psi. You can explicitly compute that thing, maybe just to start it off in the right direction. So the proof is by direct computation. And one has that you get something like this. tk acting on psi, scalar product with phi. So that's equal to all of this stuff for the integrals. And then the Vandermonde factors. And then you have the explicit action of the Hecke generator on psi. And that has the form. So all of these variables are inverted here because the inversion is actually part of the definition of the scalar product. And then I have something of this form. And this is going to be psi in the inverted alphabet, but where I switch xk plus 1 and xk. And all of that multiplied by phi x1 up to xn. So the proof carries on now by basically splitting this integral up into a sum of two integrals. So the first integral will be this one, and the second one will involve this piece. Now, for the first piece, you basically don't do anything. You just take the factor that's here and sort of directly transfer it onto phi. For the second piece, essentially you just relabel two of your integration variables. So xk plus 1, you simply change those integration variables around. And after you do that, and then collapse everything back, you find that the Hecke action has now collapsed onto phi, which is basically what you need to prove. So, okay. So this self-adjointness property, yes.
So to clarify, you don't actually do any of the integrals. You just do some massaging of the integrands.
Yeah, that's correct. This is really this is a statement on generic functions, on test functions, psi and phi, which can be anything you want. So
Okay, thanks.
yeah. Okay. So yeah, what I was saying, the importance of the self-adjointness property is that it actually allows one to start to see the traces of orthogonality showing up, and to actually help with the proof. So I'll give the main theorem now. I think this one probably deserves to be called theorem because it's by far the hardest of anything we've proved. So the functions f mu and g nu, let's say g nu star, have the orthogonality. Property that f mu scalar product with g nu, this is equal to the Kronecker delta for any signed compositions, for any strict compositions. Mu and nu. Okay, so yeah, let's make a few remarks about what's actually going on here. So the first thing is that one can see actually, at least from the explicit formula that we had for f previously, you can start to see the emergence of the poles that will play a role. So maybe let's just return to that briefly. That's here. So this is an explicit evaluation of f when you have an ordered composition. But of course, in the statement of the scalar product, I should actually invert all of these x variables. So if I do that, you'll see that this thing indeed will then have poles at the points Q inverse, YK inverse. And sort of the other family of sort of other points that are relevant are precisely the points YK inverse that show up as zeros here. So what happens in this kind of scalar product thing that we're looking at is that there's a competition going on between these two functions. So this thing is providing poles. Well, I should say the whole thing sort of boils down to these kind of ratios. 1 minus xi, yk, 1 minus qxi, yk. So this thing is showing up in both of these functions. And the exponent that it carries varies over all integers. So this can be positive or negative, this exponent. And somehow it's the competition between these two functions that is controlling the type of exponents you have here and whether you in fact have poles or not. So yeah, that's the sort of, very loosely speaking, the kind of computation that one does if one does it, say, by brute force. So let me give a quick remark on how one can.
Michael,
Yes.
I have a question about the poles. So you describe the poles in x in function of y, but there's also the poles when x's approach each other.
Yes, that's correct. So yeah, so you're referring to these poles here, or something different?
Yes, yes, this.
Okay, yeah. So indeed, it's true that depending on the order in which you do these integrations, you may have to deal with such poles. However, there is at least one distinguished way of doing this where you will not encounter this issue. So in view of the fact that Q times the contour is inside of the contour, it seems to me that if you do the x1 integration first, you will not encounter any such poles. So it's either that or the opposite. So either you start with x1 or xn, and you can do this integral first, and you will not have any issue. But it's absolutely true that you do need to pay attention to these because they definitely contribute, or they're present, I should say. Okay. Yeah, let me give a sort of very quick sketch of how the proof works. So the proof is really in two parts. So one begins by establishing a special case of the statement. And that special case is where I take f delta. So this is precisely the ordered case where we have very good control over the object. So I take the scalar particle f delta with a generic g. So one begins by establishing that this is equal to, well, now I have two deltas showing up. That's very bad. So let me change the, I don't have delta sub delta. So the indicator maybe that mu is equal to nu. Okay. So in order to do this, so this is fully factorized. We have very good control over the poles. But this one is still complicated, so it's not factorized. It's quite a bit more involved, and one needs some sort of I want to say a symmetrization type identity. Now, of course, it's not a symmetric function, so it's not really a symmetrization identity, but nevertheless, you can get some sort of formula involving sums of a symmetric group, which allow you to deal with this thing explicitly. So one begins with this very brute force integral where this is fully factorized and known, and where this thing is given as a sum of factorized objects. And one then takes that integral and actually shows by hand that this is true. So this is a kind of brute force verification. So that's step one. And step two then is the following observation. So we know that the action of the Hecker generators can be used to build up a generic F mu. So we know that F mu, we want to be able to compute this. But we know that I can get any composition I want, starting from a completely ordered one, under the action of the Hecker operators. So actually I can act with some string of Hecker operators, let's call them I1 up to IL, some number of them, and acting with these things successively on F delta, some appropriate F delta. So I can do this. And then by the self-adjointness property, I can transfer each one of these t's into the second argument. So then by self-adjointness, this becomes just F delta with T tilde IL down to T tilde I1 acting on G star nu. And the conclusion to the story is that this is sort of something I left out, but there is also a known action of Hecker operators on the G family, which should really come as no surprise. The G's are really not that different to the F's. So we know how to compute this. So we can compute this, and it just gives you a sum over, let's say, G star kappa with some coefficients, C kappa of Q. And so this is good because you're back in the situation where you know how to compute, because you have here F delta and you're acting on well, G's, arbitrary G's, but this is already handled by case number one. And so this is how you prove for generic compositions.
I'm very sorry, Michael. I think we're running out of time here.
Yeah, that's basically everything I wanted to say. So,
thank you very much. I think we have still have time for. Okay, let's thank Michael first. Thank you. I think we still have time for one or two very quick questions or comments. Maybe one quick question. Yes.
So just to summarize, is there a way of how would you use this theorem to sort of prove something about this 6-vertex model, like with domain wall boundary conditions that you mentioned earlier? Is it? Can you give some idea what you would do?
Yeah. So one application of this is the following. So we've already seen. So there was this formula, kind of eigenvector equation for the capital G's. And this one is a mu. Okay, and that's equal to, there was a product here, which I won't write explicitly, depends on X and Z. And then there is this G star nu in Z's. So one thing you can do now is multiply both sides by F yeah, it's going to be a little bit, let's say f kappa in Z1 inverse up to Zn inverse. And likewise here. So once you have done that, you can then go ahead and integrate both sides. Basically performing exactly integrals that are stated in the orthogonality. And in view of the orthogonality, this is going to be a Kronecker delta. So the summation over mu will be completely killed. And so out of this, you will get G of kappa over nu. Yeah, so now the x's are the variables of G. But there's a formula now for G as a multiple integral with this pi factor in it. And then G star nu in Z's and F kappa in the Z inverses. And that has some application because this thing here, as we've seen, this is a kind of transfer matrix for a probabilistic system. This is a transfer matrix for the colored vertex model. So in particular, this thing has a nice limit. You can take a certain continuous time limit of these x variables, where this actually transitions to the generator of the multi-species RCEP. Maybe I shouldn't say generator, but maybe like transition probability. So it's something like the probability of starting off in a state nu and finishing in a state kappa. So what this gives you now is an explicit integral formula for such transition probabilities. And under certain assumptions on nu and kappa, this integral actually becomes pretty meaningful. You can do actual honest calculations with it, asymptotics and so on. So that's one application.
I think it's time to close this session and actually the entire workshop. So thank you again. Thank you very much, Michael, for a series of very nice talks.
Thank you.
And this then, I'm afraid, concludes the entire school. I think we had some very interesting lectures, so I want to thank all the lecturers, first of all. I think we can applaud them again. And I think it's also appropriate to thank the audience, because without the audience, there wouldn't have been a school to begin with. So as organizers, we should applaud the audience, I think. Thank you very much.